Hello everybody, and I hope everyone's having a good semester, a good start to their semester, and they've got some fun classes, especially if those classes are from me. You know they're going to be fun, just like this online class, right? I'm going to try to make it as fun as an online class can be, though that's kind of a tricky thing to do. We're going to do the best we can. We've got some fun topics and interesting topics to cover. This class is relatively technical, but we're going to make it in a very understandable way. And we're going to cover all kinds of topics about water delivery systems. And hopefully by now you've taken a few minutes and you've read through the topical outline and the syllabus, and you can see some of the topics that we're going to cover. So I hope there's at least one or two in there that you might be looking forward to learning about. I think there's something in this class for everybody. Keep in mind that this class is full of students of different goals. Some are my water resource management students who are looking to find employment in either the drinking water, wastewater industries, or to go into natural resource management. We also have some students that might be interested in precision agriculture, and of course all these have something to do with delivery systems. Water is a key component in our area, and I think you'll find that it's essential to just about any place that you can find on the planet. So we're going to talk about the way that we deliver water, and we're going to cover all aspects of that. And so in this first lecture, we're going to start at kind of the very, we're not going to start necessarily at the bottom. We're going to start with the basic delivery system, and we need to spend some time, just a little bit of time on this. We'll probably spend 2 modules talking about this particular topic, and we're going to talk about pumps. Okay, so first thing we want to look at is, what is a pump? Now, I'm guessing that almost anyone, well, hopefully anyone can recognize a pump when they see it, though some of you have never maybe taken a minute to look at what a pump looks like, or to try to understand what it does. So the first thing we're just going to ask is, what is a pump? And it's not that difficult, right? A pump essentially moves water from one place to another. Now, that's not necessarily something that I have to do with a pump, right? I can take a bucket of water from a stream and I can move it from one place to another, right? But over time we found that there are more efficient ways to do these things with much less effort. So a pump is being one of those things. Either way, if we're going to move water, right, we've got to do it a certain way. The other thing we're going to do is increase pressure. Now, I can't necessarily do this through a whole variety of ways. There are a handful of ways, but a pump certainly does a good job at increasing pressure. And you're going to find, as we continue talking through these lectures and in lab, that pressure is a very valuable thing when we start talking about moving water, okay, because there is an efficiency in pressure that we don't get with things like velocity. And so we're going to talk about that as we go throughout this semester. The other thing that a pump does is it uses some form of energy, right? So we're moving some water, some fluid, from A to B. I'll probably mostly refer to water, but it could easily be applied to any fluid. Pumps are used in all kinds of settings. So for this class, we'll be discussing it in terms of water. But either way, it's going to use some form of energy, and it's going to convert that energy to perform its essential function, which is moving the water. All right, so let's define what is energy. So we need to talk about what energy is, because as we try to understand what the pump is doing in this energy conversion, it's important to understand what energy is. So we can roughly define energy as the ability to do work. Now that's not complicated, right? Right? For us, that's nice and simple. I love that. But no, some physicist or and engineer came up with this idea that force is somehow related to mass, acceleration, and displacement, right? So this work is equal to the force multiplied by the displacement. Okay, now what the heck does that mean, right? Okay, well, we can get into some pretty complicated units and jargon here, but all you really have to look at this, okay, is that work is a function of force, right? It takes force to do work, right? There has to be some amount of force applied, right? This is basic kind of Newtonian physics here, right? We're going to apply some amount of force across a certain distance. Guys, that's all this is, right? So if I look at this, I'm going to try the screen draw tool here, right? So right here, if I look at this, the force, right, that's the amount of energy, right, the force I'm applied here, which is mass times acceleration multiplied by the distance. So some force across some distance is our work, right? That's not super difficult. So it's not too difficult, right? Okay, so how do we quantify these things? We have different ways of doing it. If we live outside of the United States, we'll call these things joules, or if we're Americans, we call them foot-pounds. Okay, now that's not necessarily something you need to know. Just stick it somewhere in your head, hopefully, that a foot-pound or a joule is some unit of work. So if you see that show up in literature as you're reading things, you have an idea at least what that is. Okay, so what types of energy are there? I think most of you that have had some basic science will know that there are several types of energy, but we're going to particularly focus on two, kinetic and potential, because there's going to be a swap between kinetic and potential as energy as we go through the pump. So we're going to revisit this later, but I want to at least introduce it to you in this first lecture so it doesn't sound very foreign. All right. So let's talk about the two types of pumps we have, because the way we apply energy can be very different, right? So what we want to ask ourselves when we're looking at a pump is this a dynamic pump or is it a displacement pump? Now, you don't even need to know what these look like right now. We're just thinking about how these things operate, because we can divide the pumps into two different sections, okay? Two different classifications. And so what we're going to do is we are going to divide the pumps now into two different classifications, dynamic pumps and displacement pumps. And you don't even need to know what they look like. What you need to be asking yourself is, how is the energy added to the water? How is the energy added to the water? And that may not make any sense right now, but that's really how we classify these. Okay, if we're continuously adding energy to a pump, we are now creating a dynamic pump. Okay, we now have a dynamic pump. So energy flows continuously into the water. If we're periodically adding this energy to water with a specific volume, that becomes a displacement pump. Okay, continuous versus periodic. And we're really not going to focus a lot on displacement pumps. There is a place for them, and I'll talk about that later. If you're like me, you're a very visual individual, and so I like pictures. Alright, so in your head, ask yourself, what is this? Is this a displacement pump, or is this a dynamic pump? Okay, so look at the energy transfer. Is it happening continuously to a continuous stream of water? If it is not, or if it is, it's going to be a dynamic pump. If it is not, it's going to be a displacement pump. And hopefully by now you notice there is only a specific volume of water that is being pulled around this pump. Okay, as you can see here, this is going to go up and around, and we're applying energy just to that volume of water. So hopefully by now you have answered this question. Is it a displacement or is it a dynamic pump? And I hope by now you figured out that it is indeed a displacement pump. Alright, so let's look at the next one here. Alright, so this one we can see we have a rotating center, which is really not any different than the one on the left, but here we have a rotating center, but the fluid in this is continuously having energy applied to it. Okay, so this is kind of a handy way to think about this. Like I said, we're not going to focus a lot on these displacement pumps I'm thinking, I'm just taking a look at my lecture here. Yeah, we will just make a very short nod to these at the end of the lecture here, because we really are largely concerned about these. We're looking at large transfers of water, and a displacement pump is not very effective at doing that. Okay, so let's look at a dynamic pump. Okay, now another name for a dynamic pump is a centrifugal pump, right? So a centrifugal pump has certain parts, and when we get to lab, we will have some time to actually look at these parts and be able to identify them kind of in the real world, because here in the online setting it's difficult for me to demonstrate these things, but I'm going to do the best we can. So let's talk about these dynamic pumps first. Okay, so we have certain components of the pump which make this thing operate, and we can keep this as simple as we need to be. In the past, I spent a lot of time going over pump components and how to repair them, how to identify problems with them, and we'll talk maybe about how to identify problems with these pumps. Yeah, we'll do that for sure. But what I'm not so concerned about is that you fully understand every single component in this, because I think that my impression is that in most industries, if you have a problem with a pump, for the most part, you will consult some company or service that will take care of the problem. So how necessary is it that you understand every component here? Not so much, right? We're not going to get into the minutia of things like bearings and bushings and things like that, because I don't necessarily think it will be of great benefit to you. So let's talk about these pump components here, and they're pretty simple. What we have is we have the I'm going to call it the case, but it's really the volute. Okay, so the volute. So from here out, I'll refer to that as the volute. So you can see it's kind of round, roundish. It's more of a shape of a snail than anything. And we're going to look this in a little bit more detail to understand how this pump works, because it is critical of that. So we have this case, which is essentially the volute, right? We have a suction end, right? We have to have a suction end. We also have to have a discharge end. So water goes in through suction, out through discharge. Make sure you get that straight, right? The last thing you want to do is try to operate a pump in the reverse orientation. So make sure that you're not connecting the suction end to the discharge end and vice versa. Typically you can't, but I'm supposing you could. So let's make sure that we're not going to run into that problem. Suction end here, discharge here, and then we have an impeller. We have several different types of impellers, which we'll touch on probably in the next module. But we have an impeller. And this is not real complicated, the way this thing functions. Let me make sure I'm not skipping too far ahead. No, this is not real complicated, right? Because what we essentially have is we have water moving away from this rotating center. Those that have had one of my other classes, if you've had irrigation, you've seen the demonstration that I've done where I have a student fill a bucket with some water, and kids do this all the time, right? They put a little bit of water in a bucket and then they can swing it around and around over their head and things such as that, and the water does not spill out. Now that force has a name, and that name is centrifugal force. Okay, so the centrifugal force is essentially the idea or the notion that objects move away from a rotating center. So here we have a rotating center, and that happens to be your impeller, and specifically the eye of the impeller, and hopefully you can see that right here. The very center of that is the rotating center. That thing is moving. So you can imagine in your head water moving away from the rotating center. Now if I move that water away, ask yourself, what is going to happen? Is it going to remain void? Will there just be air right there? What does the surrounding water want to do? Here we have that whole equilibrium play, right? Because I've created an area of low pressure, right? So the high pressure coming in, right, is going to want to fill that void. So as soon as I create that pocket, right, the water coming from the suction end will go to fill it. And as things continue to move around, they will move away from the impeller, right? So it uses this idea of centrifugal force to move that away. It's actually quite brilliant the way this thing works. It's not the only thing, though, that is happening inside this pump. Okay. All right. So make sure you understand these things. This will more than likely show up on your quiz. All right. So components of a pump: suction end, discharge end, impeller, impeller eye, and the volute. Make sure you kind of understand what each of these things are and be able to label them. All right. So this is fun. Now, don't worry about all this Greek mumbo-jumbo on here. We're not going to worry about this. I had to find some cross-section of a volute, and this isn't exactly great, but it does give us a good idea of what the volute does, because each of these pieces kind of has a purpose. So if we go back here, right, we know what suction does. We know what discharge does, right? Water in, water out. We now know what the impeller does and the purpose of the impeller eye. Now the question is, why is this thing shaped like a snail? Okay, you know, that's not the easiest thing to cast in metal, right? I mean, a box would be easy. A pure circle would be easy, but to do something like this, that's very specific, and it has a very specific reason that it is this shape. So let's take a minute and explore that. All right, so here's our volute. All I've done is stolen a cross-section off of the internet, and I'm sorry it has these notation on it, but it's the best I've got for right now. So the first thing that you should notice is that the eye of the impeller, right, is not necessarily centered in the very middle of the volute. It's not necessarily centered in the middle of the volute, okay? It's kind of off-centered. So you notice that we have more area down here than we do at the top up here. Okay, so this is going to go back to our flow equation. So those that are in water measurement, hopefully this sounds familiar. If not, this will be new to you, but this is a concept that you should understand. So I'm just going to write out what that is. So bear with me, this mouse thing may not work. Okay, so Q equals V times A. Okay, that's a terrible A, but that's what you're going to get, so get used to it. Okay, so Q is the flow equals velocity times the area. So remember, the flow is not going to change. The flow is continuous, right? It is constant. Q does not change. What happens is I change either the velocity or the area, right? So if I change the area, let's just make sure we understand this concept. So if I make the area increase, okay, what has to happen to the velocity to keep this equal? You know, maybe it'd be useful to put some numbers to this. Let's just look at the relationship real quick, though. If the area increases, to keep Q constant, velocity has to go down. It's an inverse relationship. So if you're in water measurement, or if you take that class, you'll be able to see that very distinctly. But in here, I just need you to understand this idea that this is constant, and your velocity and your area are going to be inversely related. Okay, so let's keep that Q equals V times A in mind. I need some extra room on here to draw, though. So what we're looking at is this relationship here, because I think I mentioned before that we want pressure in this equation, okay? And we're not quite to the point where we're going to understand exactly this relationship. But what we do know is we do not want a lot of velocity. Now that may seem counterintuitive, right? Keep in mind, velocity is a kinetic energy, or the energy of motion. Now if I move something, if it's moved through anything other than a vacuum, we're going to incur friction. Now friction is kind of the antithesis of energy conservation, right? Because if I put energy into my water and I'm moving it, and I'm moving it very quickly, that also means I am losing energy to friction, right? We have a name for that, and we'll get there later. But friction is essentially the energy loss due to heat transfer in contact with the surrounding surfaces, okay? So we don't necessarily want velocity. So if I go back to my Q equals V times A, I'm going to have to write this up here again. Oh, that's a square. That's nice. That's not what I wanted, so let's go here. Okay. Pardon me for just a second. Okay, so let's go Q equals, I know it's painful watching me do this, but it's the best I got, people. V times A. Okay. I don't want velocity, okay? I want velocity to be down. I want velocity to be down. What do I need to do with A? Inverse relationship. I need to increase it. So this is slick, right? Because right here at the center, right, I'm going to start moving the water away. Okay, I'm just going to move it in this direction here. So as I move the water away, what is happening to the surrounding area, right? It should be increasing, right? The further I get away from the impeller, you notice the more area that I'm covering, right? So I'm going to get all the way out here to the very end. And as my water travels in this direction, you should be looking at the width of this, right? So here we've got a relatively short line. Let's keep moving this way. So our water's moving this way towards the outlet. I'm going to get over here to where it's obvious. Okay, and here I'm going to draw another line. We look at the width here. The width versus this now, this is almost double the width down here. So my area has effectively increased 2 times. And by the time that I exit the volute, I have a fair amount of area that I'm working with. So if this number is really big, right, that means this number has to go down. Right? And if the velocity is down, I have efficient energy transfer. And we're going to learn later that that energy transfer has to do with pressure. Okay? Because I'm now not using velocity to move the water, but I'm using pressure. And pressure is efficient. Velocity is not. Okay. Alright, so I'm sure I've lost a few of you now. Take some time, draw some pictures, make sure you understand this equation so that you can understand what's going on with the volute. So now you kind of understand the basic basic components of the pump and kind of what they do and how a pump works. And we'll talk a little bit more about energy transfer as we go. Let's see. Operating conditions for a centrifugal versus a displacement. This isn't too important, but there might be good information on here that you can use. We're really only going to be mostly dealing with centrifugal pumps. The nice thing about a centrifugal pump is I can close down the discharge valve to control the flow. Now, is that efficient? Not really, but I can do it, right? There are other ways to control flow. We have things like variable rate, on-demand type pumps, centrifugal pumps. With displacement, you cannot close the discharge valve, and think about this, why that is. So if I go back to this picture here, right, what would happen if I blocked it here at the discharge, right? This mechanism here, the center mechanism that's displacing this water, is going to burn up, right? The only way I can really control flow here is to change the stroke length. So I can create a bigger stroke to draw more water, or a smaller stroke to draw less water. Okay. Clear as mud, right? So operating conditions, yeah, don't worry, just focus on the things that I mentioned there. Pump types, we'll get into this maybe a little bit. There are different types of dynamic pumps. We have end suction, split case, vertical turbine. We have some special use ones like jet pumps, regenerative turbines, vortex pumps. And we'll talk about those maybe a little bit, just so you can identify what it is by looking at it. We're not going to go into the fine details, because some of these can get very, very complicated. We will maybe talk about why they're special and what makes them different. Displacement pumps, we have reciprocating, we have piston types, diaphragm types, rotary types, peristaltic, progressive cavity, multiple gear lobe. There's a handful of these, and they're very specific. We see them in the medical industry. We see them in the environmental industry, which is why I'm bringing it up here. Peristaltic pumps are very commonly used when sampling from wells or from water that you don't necessarily want to degas. Okay, so let me kind of go back so that makes sense, because there's some of you that are interested in going into the environmental side of things, and I want you to make sure you understand this. Okay, so if I look at this displacement pump here, you notice that I can draw water through this tube without introducing air. This thing will degas very quickly because it's rotating very quickly. The energy is applied rapidly. So if I'm interested in analyzing things like volatile organic carbons, which many of them are carcinogenic, things like pesticides and various things which will volatilize, they'll evaporate. If I have this centrifugal type system, I can sample quite effectively with a peristaltic pump. I'm just going to tell you they are a pain in the neck to use, often requiring priming. Yeah, I'm hoping there's better ways to do it now than there was, and there's better technology. I'm sure there is. It's been a while since I've used one, but some of the ones I have used have been clunky. But again, we see this in the environmental field, environmental monitoring, as well as the medical field, and I'm sure there's a handful of other places that do utilize it. So I want to at least give it a nod. Okay, so there's our two pumps. We know our parts. We know what the impeller eye does. We know what the volute does. We know that there are some specific operating conditions, and then we have some pump types which we might get into looking at. Okay, so I think that's probably good for this week. I've probably completely overloaded with you. I will make sure that this lecture is up on Canvas in your module, so if you want to refer to it as you're doing your quiz, please feel free to do that. And if you have any questions, don't forget to post them in the discussion board. Thanks for listening and for following along, and have a good week.